Okay, hello. So our topic today is Ranjitakata methods. Okay, so in this case, we first of all, I think I have some brief introduction of that in the last lecture, and we can start from the Euler's method. Okay. So for Euler's method, what we can do is so the Euler's method equation is this yi plus 1 is equal to yi plus f of xi h yi times h. So for example, if we have a function, okay, something like this. So we take the value of the function at xi, so which will be f of xi yi, okay, and then we need to take a slope of that function, okay, so maybe slope in this direction, okay, in this direction, and then that slope will determine the next point on the curve, and that next point on the curve will be the estimate. So if the next point is say xi plus 1, okay, so the point on that slope line, the point on that slope line will be considered as the point on the curve. So this will be the point. This will be the so this point then can be calculated as this intercept. Okay, the intercept plus the initial value plus the change in this vertical distance. So here we have yi plus 1 is equal to yi plus f of xi yi into h. So in this way, we can represent it. Okay. So where h is the uh, difference between the two x values, xi plus 1 minus xi. Okay. So this formula is referred to as the Euler's or Euler-Cauchy or the point slope method. So a new value of y is predicted using the slope equal to the first derivative at the original value of x to extrapolate linearly over the step size of h. So this is simply the method given by the Euler for this numerical solution of the ordinary differential equation. So let's apply this formula, apply this method to find the numerical integration of d of this differential equation. Minus 2x cubed plus 12x squared minus 20x plus 8.5. So if we have this equation, so for example, dy over dx is equal to minus 2x cubed plus 12x squared minus 20x, 12x squared minus 20x, and then plus 8.5. Okay, so can you hear me, and also can you see this screen where I am writing?
Yes.
Okay. So in this case, if you want to find its analytical solution, so you will integrate it. So in this case, then what you will find is minus 2x power 4 over 4 minus 0.5 x power 4. and plus 12x cube over 3, so that will be 4x cube, minus 20x square by 2 minus 10x square, and plus 8.5, and then plus c. And for the initial conditions, which are given, are like this. Initial conditions are when x is equal to 0, y is equal to 2. So this is also given in this question. X is equal to when yeah, so the initial condition is x is equal to 0, y is equal to 1. This is the given condition. So y is equal to 1. So if we apply this initial condition, then the final solution is y is equal to minus 0.5 x power 4 plus 4x cube minus 10x square plus 8.5 x and 8.5x, and then because when x is equal, so c is equal to c will be equal to 1. Okay, so this will be the final solution. So this will be the analytic solution, analytic solution. Whereas the numeric solution will be, in the numeric solution, you will have a table of values. So for example, if we have x value, and then correspondingly, we will be able to find the y value. So numeric solution is like this. Okay, numeric solution is like this. So in this way, we can plot the analytic and numeric solution. So numeric solution will be a smooth curve in this case. Okay, whereas the analytic solution will be the combination of the points. Okay, will be the combination of the, so we will get the numeric solutions only at the points. So analytic and numeric solutions. So we will have these values, we will find these values. So the numeric solutions we will find by the Euler method firstly, which in fact is the member of the Range Khata family of solutions. Okay, so for the Euler's method, we have this basic equation yi plus 1 is equal to yi plus f of xi yi and times h. Okay, but remember that is f of xi yi is actually we can find from this equation. Okay, because this is the given equation, dy over dx is equal to f of xi yi. So in this case, this initial solution differential equation is given in this form. Okay, it is a function of x and y, although in this case it is only a function of x, but for the more general case it can be a function of x and y as well. So here we can use both the values of x and y. So that means we can determine the fx of yi needed for this Euler's method from this equation, and then we will input it into there, and then we can find the value for the next point. So for example, from a point of, if the initial point is 0 and the increment that is h is 0.5, so then we can find the value of y at the value of x is equal to 0.5 by only inputting the values at x is equal to 0. Okay. So in this way, how the Euler's method works. So in this example, so first of all, uh, we will find out the value of y. Uh, we will first input the values into the equation. This is the Euler's equation. So y 0.5 is equal to y 0 plus f 0 1 and 0.5. So f 0 1, because this is the given initial condition, because at x is equal to 0, the value of y is equal to 1, and times 0.5, this is the interval which we will take. So we have to uh, calculate the values of this function at x is equal to 0 to x is equal to 4 at an interval or a step size of 0.5. So if we start from 0, the next step will be 0.5. So that's why it is 0.5 over here. 0 and then from 0.5, and then h is in itself is the interval. So so we know that y0 is 1. This is the given initial condition. And the slope estimate at x is equal to 0, we can find from the original equation. Okay, so dy over dx is actually the function of x and y. Okay, so dy over dx is actually the slope. So we need to find the slope, which is in fact the function of x and y. So we can input the value of x is equal to 0 into this function, and then we can find the value of 8.5. So in this way, then if we input the value of f01, f and y0 into this equation, we can find the value of 0.5, which will be 5.25. 5.25. So this is the value which we got from the Euler's method. However, in this case, since we already know the true solution, that is the analytic solution, so from that analytic solution, we can even find the value of true solution. And for that, we need to input the value of x is equal to 0.5 into this solution equation. And when we input this value of 0.5 into over there, we get a value of 3.21875. So the true answer is 3.21875, whereas the predicted answer is 5.25. So which means that the error is uh, true answer minus the predicted answer is minus 2.03125. In percentage terms, this is an error which is about 63.1%. Okay, so uh, you can see that although we have used the Euler's method, but there is an error in the answer. However, we can reduce this error by taking the smaller step size, and later on we can even do some modifications in the method itself to reduce the error. So, but as a starting point, we can see that how we can calculate the values of y, values of the function using the Euler's method. So this process can be repeated for the next step. So that means by this process, we have first found the value of y at x is equal to 0.5. So since the step size is 0.5, so the next step will be at y is equal to 1. So for y is equal to 1, we will use the previous step. Y is equal to y at x is equal to 1. We will use the previous step y at x is equal to 0.5. And in this case, the values of the slope will be calculated at 0.5, and the previously calculated value of 5.25, and then 0.5. So in this way, then f of 0.5, 5.25 is calculated by this original equation. and then input into this, the values are input into this equation, and then uh, uh, from the Euler's equation, we get the value as 5.875 for the next point. However, the true solution at x is equal to 1 is actually 3. So there is a difference, 3 and 5.875. So the relative error is 95.8%. So we can see that as we go along, for all the steps in this first case, the relative errors are quite appreciable. So here we can see that we can tabulate these values for x is equal to 0, 0 0.5, 1, and then we can see that their errors are 63.1, 95.8, 131%, and etc. So these are called as the global errors. There is some local error as well, which I will talk about later on. But the global error means it is the error of not only the uh, uh, current step, but also the cumulative errors of the previous steps. So in this case, you can see that the global error has first increased up to the third point, then it start decreasing, okay, and then it increasing, then it increased again. It is because I think in some of the cases the errors are positive, and some of the cases the errors are negative. So when we add them together, positive and negative errors, so the global errors will fluctuate. Okay. So if in the first step the global error was the error was negative, in the second step the global error was also negative. So the combined effect of them will be a larger global error. So in the fourth step, the error was positive. So the previous negative error and the current positive error will cancel with each other when we add them together, and then their global error from this uh, from this third step to the fourth step will decrease. Similarly, from the fourth step to the third step, to the fifth step, it is decreasing. So uh, this is how we can explain the change in the global error. So let's see how we can apply this method on the spreadsheet. So for example, if we want to apply the Euler's method using the same equation, so we will have the x, we will start from the x and y values. So initial values of x were x is equal to 0, y was 1. And then next we can calculate the f of x and y. Remember that f of x comma y. Remember the equation of the Euler's method is this. So this is the equation of the Euler's method. Okay, so in this equation we need the value of y and f of x I, y I. So for the values of f of x I, y I, so we need to input the values into this equation. The original equation is this. So okay, so if we input the value of x is equal to 0 into this equation, then we can find the dy over dx, which is basically the slope which we need over here. Okay, into this method. So we can input it like this. So it is minus 2 times x cube plus 12 times x square minus 20 times x and then plus 8.5. So in this way we get a value of 8.5 over here. So once we have these values yi and then fxi and then we have the value of h, we can find the next value of yi plus 1. So that means the refined estimate can be found over here into this cell. So let's add so for h, the h in this case we are taking as 0.5. Okay. So let's calculate it. So the next increment of the next value of x will be equal to the previous value of x plus h. So this is h. So I will input into this formula. And the next value of y will be equal to the previous value of y. Okay. Plus previously calculated fxy value and multiplied by the constant value in this case, which is h. So in this case, now we can calculate it as 5.25. So again, we use this 5.25 value into this equation to calculate the new value of f of xy. So in this case, then now we can find that the values of f of xy is 1.75. So now our table is complete. I can just select it and then drag it down to add a few more values. Okay, so here. So in this way, now where I can very easily get these answers. Okay, so 0, 0.5, 1.5, 2, 2.53, and then 203. So if I compare my answers with these answers which have been tabulated over here, so I get these 1, 5.25, 5.875. That for 4 it is 7. Okay, so probably I made some mistake over here. Some mistake has been done. So it was 8.5. So it is yeah, I think the mistake is here. It was minus 2x cube. It was minus 2x cube plus 12x square minus 20x plus 8.5. So yeah. Yeah, now the values are correct. Okay. And then so this is the y value, so we can indicate it by the y Euler. And then what will be the y true? Y true. So for the true, we have this true solution here. For the true, we have this true solution is here. Here. So for true value, we need to input it into this over here is equal to minus 0.5 times x power 4 and plus 4 times x cube and minus 10 times x square plus 8.5 times x and then plus 1. So it is y true is 1. And then similarly, I can calculate it for all the values of x. And then this is y true. So the error is true value minus the values calculated by the Euler's method. So for the first one is 0. because that is the initial point. For the second one was minus 2.01 and then minus 2.8 and then like that. So the percentage true error, that is the uh, percent error, okay, percent true error in this case. So the percent true error in this case is equal to this uh, error divided by the true value, okay, and then we can express it in the percentage notation, okay. So it is the 0%, and here it is minus 1. So we get the same answers over here for the global error, okay. Uh, okay, so this is the percentage error over here. Okay, so what we can see over here is that we get the this percentage error. Okay, so we can plot these values, okay, and then we can see that there is a big difference between these two curves. So this is the true solution, and this is the solution by the Euler's method. Okay, so there is a big difference between these two curves. However, this solution can be decreased by the further refinement. So note that although the computation captures the general trend of the true solution, the error is considerable. So this error can be reduced by using a smaller step size. So we can reduce this error by using a smaller step size. Okay, so let's see how we can reduce it. But that we will see later on. First, let's do the error analysis for the Euler's method. Okay, so the for this Euler's method, the error comes from two sources. So one is the truncation error. One of them is the truncation error. The other is the one of them is the truncation error. The other is the round off error. Okay. So the truncation errors are composed of two parts. The first part is the local truncation error, and the second part is the global truncation error. Okay, so this global as earlier we have found out this local truncation error. So this local truncation error can be found from the uh, Taylor's series equation. Okay, so from here, if you remember that in chapter number chapter number 4, we have said that we can represent these functions by their Taylor series. So, for example, yi plus 1 can be represented as yi, which is the initial value, plus the y prime of I, that is the first derivative, times h, plus y double I over 2 factorial into h square, etc., like that. So if we compare this equation with the Euler's equation, so we can see that the first two terms represent the Euler's method. Okay, the first two terms represent the Euler's method, and the remaining terms, which we do not represent in the Euler's method, these are the error terms. Error terms. Okay, so conveniently we can represent these terms as like this. Okay, so the error in the Euler's method is equal to the second order or higher terms, and this error then we can estimate. So it is actually uh, the the local error comes from this Euler's method. Okay, so for example, this 63, in this case, we have already calculated the global errors, but how we can calculate the local errors? So that we can do by considering the Taylor's series. Okay, so in the Taylor series, we can apply this equation. So for example, let's apply it for this current problem, okay, which we just discussed in example 25.1. So we can write the error for this Taylor series. Remember that the first two terms of the Taylor series are included in the Euler's method, but the remaining terms in the of the Taylor series are not included in the Euler's method. So for the given problem, uh, which is a polynomial form of the, that is this problem which we have just considered, which is a polynomial form of the, which is a differential equation in the polynomial form. It is a third order polynomial. And if you can, if you think that the polynomials, if you take the derivatives, and then after some point taking the derivative of the polynomial, the derivatives will become zero. So in this case, from x cube, it will be and then it will become x square, and then it will become x, and then from x it will become 1, and then from 1 it will become 0. So we need only a specific number of terms to find the error in the case of the polynomial. So in this case, we only need three terms: f prime, f double prime, f3, and these terms. So here, if you see that the Taylor series over here, it starts from the initial value of y, then the uh, function itself, okay, that is initial value of y, that is considered as a constant, and then the function itself. In this case, the function itself is the given derivative function, and then the first derivative, and then like that. So the error will start from the first, second, third, and fourth derivative terms over here. So in this case, example 6.2, we can apply this equation. So we can take this equation over here, and then we can find out that gradually their uh, derivatives are like that. So let's put these derivatives into this Excel. So this is the equation. So if we first put this equation into Excel. Okay, and then we have okay, so okay, so maybe we can now add these values over here. So first, let's calculate the f prime xy. Okay, f prime xy. So it is the same example which we are continuing to find the local error. So for finding the local error, first we need to find the f prime xy. Okay, and then we will need to put these f prime, f double prime, f3 into this equation, and then we can find these errors over here. So f prime xy will be equal to, it is given by minus 6x square plus 24x minus 20. So it is equal to minus is equal to minus 6 times x square plus 24 times x minus 20. Okay, so this will be f prime of x. And then f double prime of xy, it will be equal, it will be given by this equation, minus 12x plus 24. So these are, remember that f prime of x y will be the derivative of this equation. Okay, if we take the derivative of this, because this we are taking as a function into the Taylor series. So now it will be equal to minus 12 times x equal to x, and then plus 24, and then f triple prime of xy, that the value is a constant. That value is a constant. After that, it will, all the terms will be 0. That means whatever the error that will be introduced, that will be the sum of the errors by calculated by these three terms. Okay, so we can just add a few more columns over here. So now we can find the errors. Okay, so you can say that the error 1, error 2, error 3, and then we can find the uh, total error. That will be the actually the local error. Okay, it is not that the total error. Okay, that will be the global error. So here we can find the total local error. So let's find first error. So for this first error, we need to input into this equation. So here we need these 2, 3, and 4, 2, 3, and 4. So I can temporarily put these numbers 2, 3, and 4 over here to use in our calculations. Okay, so here I can put like, so it will be the f prime. So it is equal to this value multiplied by h square. So h is what? H is here, this one, this value, that is here, and then square I will take from here. Okay, so it will be this value. So it will be this value, right? Okay, so it will be minus 5, and then here it will be um, e2, error 2 will be equal to, no, but here I think no. Okay, so this value is error 1 will be equal to this f value multiplied by h. H value is this square. So square we will take from here. Okay, and then that will be divided by the factorial of 2. Okay, so factorial I will use the fact function, factorial of 2. So factorial of 2 is here. Okay, so it will be minus 2.5. And now the error 2 will be equal to this f double prime multiplied by h cube. So cube I will take from here and divided by factorial of 3. Okay, factorial of 3. So yeah, it will be the factorial of 3. So I will be okay, and then the last error is here. It is equal to f triple prime, which is minus 12, multiplied by h power 4, h power 4 I will take from here. So this, and divided by factorial of 4. So 4 I will take from here. and then this. So now I can add up all these three errors. So I will get minus 2.03125 over here. So which will be the local error over here. So now what I can do is I can just copy it down, okay, and then find these errors, and then I can copy it down. Hopefully it is correct. So this is the true error, okay. So the percent local error percent local error will be equal to this this is the local error, okay. So this is equal to the this error divided by the uh, what is divided by the true error, okay, true value. So the true value is here. So yeah, actually one thing is one thing which we need to I have missed is over here is that uh, these error estimates are not for this value. These error estimates are for the next value. So I will just shift these values, and then the last one will be, I will delete it, okay. So these will be the error estimates. So now the percentage local error will be equal to this divided by the true value, which is over here, which is now over here, it is minus 63.01%. And if I represent it in the percentage terms, so here I should get it. So now I can see that it is the same, I think almost the same answers which I got over here. Here one thing has changed, because this F3 should be minus 12 throughout, so I should correct it. Okay, so because when I copied it down, so by the format of Microsoft Excel, it changed its values. So now I got these values. So minus 2.5, minus 63.1, and minus 28.13, minus 1.41, and like that. So are these the same values which I got before? So here, here. Yeah, so minus 63.1, minus 28.1, minus 1.4. Okay, so minus 63.1, minus 28.1, minus 1.4, 20.3, 17.2, okay, 20.3, 17.2, 20.3, 17.2, 3.9 minus 11.3, 3.9 minus 11.3, and the last one is minus 53.1%. Last one is, so we got exactly the same answer. So here now we have, you have found out that what these percentage local errors means, okay? Percentage local error means. And then if you want to confirm the global error, so the global error is this, whereas the global error is this. So the global error is the sum of the this local error, and then like that, okay. So here in this way, then we have found out the local error. So if we look at again this example 25.2, so this is how they have found these errors: minus 2.5, 0.5, minus 0.3125, as you can see that the errors keep decreasing. Okay, higher the term is, the error keeps decreasing. Okay, so this way then you can estimate the local errors as well. Okay, so the effect of the reduced step size on the Euler's method. Okay, so the next example is effect of the reduced step size. So earlier we used a step size of 0.5. If we reduce the step size to 0.25, then how does it work? So for this, now we can, since we have set up this sheet, I can just make a copy of this sheet, okay, to save time. So I have made a copy of this sheet, and then in this sheet, I can now change this step size from 0.5 to 0.25, okay, and then see what happens. So now I can see that at 0.25, we got these types of percentage errors, okay, and here you can see that 0.5, the percentage errors were more, okay, so it is 0.25. So now I can further expand it to say 4, okay, and then I correct it here, it is -12 throughout, and then you can see that these are the percentage error. So in this case, if I see over here, where is this global error? Yeah, this is the global error. Yeah, this is the global error over here. So if I take the average of the global errors over here in this 0.25 step size, the average of the global error is now about 37.4%. 37.4%. Whereas in this previous case, in this previous case which we calculated, the percentage global error was quite high. So it is minus 80.1%. Okay, so from 80.1% to it has reduced to minus 37.1%. Similarly, the percentage local error was about minus 14.44%. Okay, so but here in this case, the percentage local error, the average percentage local error is now about 3.5%. So there is a great reduction in the local and true errors. So we can even plot these values. So for example, the values of X and the values of Y, okay, for a case of 0.25, okay, for a case of 0.25 against a case of 0.5. And then we can see that by reducing the step size, the curve for a smaller step size comes closer to the true solution. It comes closer to the true solution. So by increasing the step size, this curve will come closer and closer to the true solution. So this we can verify it after by plotting this curve as well. In fact, I did it as well when I was doing it. So here I have plotted these curves. Okay, and then you can see that this was the curve for the true point, this was the curve for the 0.5h, and then this was the curve for 0.2h. So the curve has come closer to the true value. So it's a very general solution that this by increasing the step size, we can improve the accuracy of the method. Okay, so today then we have covered these 3 examples. So next we will talk about the improvements in this Euler method. Okay, improvements in Euler method. So just a very brief in this Euler's method. So for example, if you look at this Euler's uh, method over here. So in the Euler's method, we use the initial slope over here to estimate the value for the uh, solution. However, if we, instead of taking the initial slope, we take the initial and the final slope and take the average of that, we can improve this value. So this is one type of improvement. Another type of improvement is that instead of taking the slope at the beginning of this interval, we can take the slope at the mid of this interval. So that can also improve this method over here. So these are the true improvements, and then we will further discuss about the more general Ranjakatha methods in our next lesson. So in this way, then I think we will complete this topic in the next week. So in the next class on Friday, you are going to take the quiz. Okay. So